So, so I tried to, if you were way off, I tried to point out to some reference later in Polchinski book. And if it doesn't help, please come and see me. Okay, come and see me, and you know, we can sit together and talk. And also, it relates to other questions. The best time is Tuesdays, so Tuesday after 3 o'clock, between 3 and say 5 or something like that. Just pop up in my office and we'll chat. But as I said, you know, marks should not be your concern, right? The purpose is that you know what we're talking about. Okay.
Oh, just a quick question. Where do we go exactly to pick up our exams?
Not exams. Don't be so serious.
Did I say exam?
No.
I meant assignment.
Yes. So Leanne, do you know Leanne? So it's a 3rd floor. So she sits as you walk to the kitchen. You know, on the left there is an office. Leanne came.
Okay.
So she has. I figured that given that there are people from various places, that would be the best way to do it. And then I don't have to waste time in class. What's everything? All right, guys. Good morning. Just saying, the homework is with Leanne, and you know, you can pick it there. And those who are interested only in the mark, just write me an email, and I tell you the number. But you should see. Okay, to see. All right, guys. So so let's go back and pick up where we discussed. So we talked about a new type of CFTs and free CFTs, and we decided we'll concentrate on this BC system. So that's a holomorphic CFT. So this is a holomorphic CFT, and it's given called X 1 over 4 pi to the del bar C. And so, so in principle, we will start with the fields B equal a function of Z and Z bar. C is also a function of Z and Z bar. But you can see just by looking at the equations of motion that del bar C must be equal to 0. So those are classical equations. When I vary with respect to B, and when I vary with respect to C, I will get del bar B equals to 0. So in fact, that's the reason why it's called holomorphic CFT. So the fields B and C depends only on that coordinate. So that's kind of a special CFT because B and C are not bosonic fields, and they are actually anti-conjugate. So BC equals minus CB. And then, you know, we have to think about B and C as being a tangent fields, right? A primary field of our CFT. And so we have to assign conformal weights. And the point is that given that they are holomorphic, they carry only holomorphic weights. And so we decided to make it lambda 0, and then H 0 equals 1 minus lambda 0. And then what I did, I argued, gave you a hand-waving argument that that's actually the nice assignment, given that the weight of the action is 0, 0, which is what you need at least for classical scale invariance. So what we proceeded after that, we started deriving quantum equation of motion. And from quantum equation of motion, we can get contractions, right? And so in order to derive quantum equation of motion, so what we've been doing, so we look at the path integral. I'm just reminding some of the stuff we did last time. So we look at the path integral of this type, and then we do a variation. We do a variation with respect to a C field. So the general argument that once we vary the functional derivative, we should get 0. And so if we are careful, then we will get something like minus 1 over 2 pi del bar b times c plus delta function delta bar. And so from here, we introduced our normal ordering. So we introduced BNC normal ordering in such a way that a normal ordered product of operator satisfies naive equation of motion. So a naive equation of motion would be that there wouldn't be any delta functions there. So we have to actually add additional piece in the equation of motion that will cancel that delta function. And we discussed last time that that piece was 1 over that one too. Okay, so finally, let me just, so from here, we conclude that a contraction of B and C, so this guy, this depends on, C depends on Z2, is 1 over Z1, 2. And then C of Z1, B of Z2 equals also 1 over Z1, 2. So I'm just keeping track of the leading singularities, and so there is twice the sign flip, one because I anti-commute B and C, and the other sign flip because Z1, 2 by definition is just Z1 minus Z2. And so, so those are the right contraction. So also what we discussed last time is that that's only if there is a non-trivial contraction between B and C, and BB and CC doesn't have any singularities. Okay, so that was our endpoint. So, any question?
What is the physical meaning?
CFT. You will we will talk once we will get a little bit more familiar with the CFT, and I will explain why it is actually crucial for us, and why do we need to understand it. So our next step is to construct the stress energy tensor, and once we will know what the stress energy tensor is, we can actually go ahead and build up the whole structures here. And so what I'm going to do is I'm going to spit out the answers for the stress energy tensor. So I'm going to take an approach that I'm going to define a stress energy tensor, demonstrate that with this stress energy tensor, so in some sense you have to think of the stress energy tensor as a fundamental object. And so once I'll show that it has the right OPE structure for the stress energy tensor, and in particular, this field assignment that we came up with, the conformal weight assignment, will follow directly from the OPEs with my stress energy tensor. So, so I'm going to say that TZ equals del BC minus lambda del BC. Okay. So the first del acts only on B, and the other del acts on the product BC. And everywhere as before in the definition of the stress energy tensor, I use normal ordering. Okay, so that's a holomorphic part of the stress energy tensor, and I'm going to take the anti-holomorphic part to be identical to 0. By the way, everything that I'm saying, so we look at a holomorphic BC system, but everything that I'm saying can be done also in the anti-holomorphic setting as well. So just pretty much replace everywhere you see that with that bar. Okay, so the first thing we want to do, we want to see that given that definition of the stress energy tensor, our B and C fields have the right conformal weights. So let me remind you that if I have a tensor field O, then the OP with the stress energy tensor must be of this type. So I have A squared Z squared O plus 1 over Z del O plus non-singular. So does everybody understand, the indices here, right? So by writing this, I'm assuming that I'm inserting the operator at 0, this one I'm insert at z, and so that's the difference. But of course, in general, I could put z1, z2, and the generalization is obvious. Okay, so let's go ahead. So we know what are our contractions, and let's compute OPE with the B field and see if it's actually a Hansen field. Okay, so we have, this is given by del BC minus lambda del BC. Okay, so that's my stress energy tensor, P of that, and then I have B. Okay, so in order to get the conformal weight, I have to look at the field. I have to look at the largest singularity in the OPE. Actually, in the case of a primary field, it's 1 over z squared singularity. So you can see that from this term, so the only way I can contract C field and B, and that will give me 1 over z singularity. Is that clear? Right. But let me still write it down. So I will have del B, right? Del B divided by z, and this guy sits at 0. So that's the only piece that will come up from the first term. So let's see what we will have from the second term. Right, so from the second term, so here there are actually two terms here, right? So the first one, when del acts on B, then I will have to contract C and B. So I will have minus lambda del B at 0, right? And then C and B, when I contract, gives me 1 over z. Okay. For the other piece, when del acts on C, so I will have B left. So I will have minus lambda B. So let me write it down as B of z. So notice here I could have put z dependence and considered further Taylor series expansion of that, but that would not that will produce non-singular terms only. So I'm only concerned with the singular terms, and it will be clear in a second why do I have to keep B of z here. Okay, so I have B of z, that will come up from this guy, and I have del C. So I have del C B, so that will bring in del 1 divided by z. Okay? So what do I have? So I have 1 over z del B, right? So I have 1 minus lambda, okay? And right now, I'm just keeping track of any possible non-singular terms. I'm not dropping anything. So then I have minus lambda, and I'm going to do a Taylor series expansion of the field B. So I'm just going to write it down as B plus z del B. Okay, so any other term eventually will not contribute, and del of z guy will give me minus 1 over z squared. Okay, so you can see now that if I keep only non-singular terms, so the largest non-singular term will be of the type lambda over z squared times b, right? And then there will be additional 1 over z singularity. So there is a piece here, and then there is additional piece that will come up from when we expand the field in a Taylor series, right? So that will come up with a plus sign, and so I will have plus 1 over z del b 1 minus lambda and plus lambda, okay? And then I don't have to write anything because this sign indicates that I care only about non-singular terms. So you can see that the singularity, the OPE with the stress energy tensor gives me the structure, which is exactly the one expected for a tensor field of conformal holomorphic weight being equal to lambda. Okay, that's exactly what we want. So in the next homework assignment, you would have to do some of the exercises. You have to get familiar with deriving OPEs and understanding a bunch of that. I think it's very useful knowledge. So the things that you always have to keep track is that when you are extracting terms, sometimes it's not enough just blindly contract everything. That will simply give you the largest singularity. So you will get only this piece. But it's easy to make a mistake unless you do this, because then you will get 1 minus lambda in a subleading singularity. And that's simply not right for the OP of primary field. All right, guys? So we did for B. Now we're going to do exactly the same for a C field. And with the C field, I'm not going to care now about keeping track. You can be as careful as I've been before. So instead, what I'm going to do, I'm just going to look at the leading singularity and show that that indeed corresponds to a conformal weight 1 minus lambda. So what do I have? I have again del BC minus lambda del BC, okay? And then I have to contract it with C. Well, so you can see that the contraction comes with del B and C, right? But I have to anti-commute this C with this one, so there will be a minus sign, because there is a minus one, because I have to anti-commute those two C fields. And then B and C gives me 1 over Z, but there is a derivative active of that. So I have minus 1 derivative of 1 over Z. Okay? And actually from here you can see that you are left with the field C. So now if I look at the second term, right? So again, there are two possible ways. To make a contraction. One contraction when del acts on C. Then you have BC contraction, but that will be only 1 over Z singularity, right? And I told you I only care about 1 over Z squared singularity. That's enough to get the conformal weight. So the way we're going to do it, we're going to contract. We're going to act with this del on B and leave C untouched. And then we have del BC contraction, so it will be plus lambda del 1 over Z. There is a sign flip again because I have to anti-commute the two C's in order to make a contraction. So we have lambda minus lambda times 1 over Z squared plus 1 over Z squared C, which is 1 minus lambda Z squared C plus some leading terms. And so again, just from the general structure of OPs, you conclude that the conformal holomorphic weight of C is 1 minus lambda. Okay, so I like particularly this way of thinking about the CFT. So in principle, I didn't even need the action. And in various examples, when people study CFTs, there is no explicit action given or presented. In fact, you can think in terms of the whole structure, kind of think about CFT in an algebraic setting, thinking about OPEs and fields. So we will develop, there is a deeper relation which we'll discuss later. Okay. So any questions at this stage? No. Good. So next step, as for any good CFT, this one also has a stress energy tensor. We would like to know what's the central charge of this CFT, right? So let me remind you that the only CFT we know so far is the CFT when they have D3 fields on a roll sheet. Okay, and so here remember that we're talking about Euclidean roll sheets with flat metric, and so in that case the central charge was simply D. So each single free scalar field X was having a central charge 1, so when we have D of them, the central charge is simply D. Those are decoupled CFTs, right? So that's the way you have to think of this, is that there is a CFT for each scalar field, but they do not couple with themselves, they are free. Okay? and the central charge is simply F together. So, so what we would like to do now, we would like to do exactly the same exercise here, and we would like to ask the question, what's the central charge of the DC system? So question, what is central charge of DC system? And then I will be able, after we do that, then I will go back to Alex's question, and we will discuss why do we care about this. Okay, so we know how to do it, right? So we know that in order to compute the central charge, we have to look at the 2-point. So we have to look at the OPE of the stress energy tensor. And so we know that there will be lots of terms here. So the first one is actually a conformal anomaly piece. So it's C over 2Z to the fourth. And then there are two more terms. There is Z squared T plus 1 over Z del T plus non-singular. Okay? And so I'm not going to do the full exercise, and that's actually a good thing to get familiar with OPEs in this system in order to derive these terms, right? So what, in fact, we're only going to be concentrating on, we're going to be concentrating in the OP of the most singular term, because that will give us directly the information, what is the central charge. And so, as we discussed before, in order to get the most singular term, we need to do as many contractions as possible. Okay, so let's go ahead and do the computation. So I have T3, right? So that's equal to del BC, and then I have minus lambda del BC, and then I have del BC, okay, minus lambda del BC. Okay, so there is a new element in the analysis that come in here, and so I wanna use this exercise in detail. Okay, so again, remember that this guy lives at Z, and we put this guy living at 0. Okay, so but of course, as I mentioned before, you have to think about Z1 and Z2 and stuff like that. Okay. So, so there will be, you can see that there will be 3 different contributions, right? So there will be a term of this type, del BC, okay? So then there will be a term, of the following type. There will be a factor of 2. Note that because I always have a pair of fields, so if I anti-commute the pair, I do not make any sign change. So there will be just a factor of 2 coming from OP here. So I will have minus 2 lambda del BC del BC. Okay. So you can, if you don't trust me on that, you can do it carefully, and you will see that that's indeed the case anyway. And so finally, there is a third term when I contract those two ends together. So that will be give me lambda squared del BC. Okay. So let's look at each of those terms separately. Compute the leading singularity as a multiplier, and that will give us. So let's look at the first one. So the first one is del BC, and then I have del BC. So this is kind of the simplest one. Well, so let's see. So what I'm going to do, I'm just going to contract this guy and this guy, right? And so so B and C contract. I can anti-commute, but I have to anti-commute twice. So there will be a plus sign. Okay. There is a plus sign, and then when I can B and C gives me 1 over Z. Okay, but I have to act with the derivative on Z. Okay, so I have del 1 over Z. So once I did that, I'm still left with these two fields. left uncontracted. So actually this term is already singular, and so it will contribute to the OPEs at the subleading singularities, but we don't care. We want to get the leading singularities. That's why we need to continue contraction further. So what I claim now is that, well, again, you see C and B, that's 1 over Z. But actually, and then there is a derivative. But what I claim is what we have here is minus del 1 over Z. Okay, so this is the new aspect that I'm talking about. So is that clear why there is a minus 1? Somebody can tell me why there is a minus 1. Sorry? No, that's not, because C and B are the same 1 over Z. That's not the reason. Maybe that's you did say anyway. But let me go. You want to add to that something?
Well, you want to contract C with del B, right?
Yeah.
And so you need to flip it in order to use the same thing as before, which gives you minus the line.
Okay, so let me tell you. So this is 1 and 2, right? So what I have is derivative acting on del 2, and then I have 1 over Z 1, 2. But that's the same as minus derivative acted on 1, that's 1, 2. Okay? So that's a minus sign comes from here. Some of you maybe, when you were saying what you were saying, maybe you meant that. Or equivalency. But is that clear? Yeah. Okay. Right. So, and remember, because I always put Z2 to be equal to 0. So that's why I have, in principle, I could have written carefully Z1 and Z2, and there would be no question marks. All right, guys, so what do we have? So we have minus, this guy gives me minus 1 over Z squared, minus 1 over Z squared, so it gives me 1 over Z fourth. So that comes from contraction there. You want me to do in such details the other ones or not? We can do more in class if you allow me to skip some steps. Okay. So again, the point is that I am telling you all what is necessary is that you should be able to do the rest. There is no subtleties whatsoever afterwards. Well, okay, let me do one more. Let me do this one, and for the third one, I am just going to write down the answer. So for the second one, I have minus 2 lambda, right? And so let's see what do we contract here. So here, there are actually 2 terms, right? Because the derivative here acts on B and C. And I have to make 2 contractions, because there will be 2 terms here. Let's look first at del B, right? When I have del BC, then I have del BC, del BC. That's exactly what we computed before. So that gives me minus 1 over Z. Right? And so then there is another term, which is B del C. Okay? So, right? So the other term, okay, I apologize, but that's not right. So 2 is not equal to 2 because we already read the piece. But I want to now look at this OP, B del C del BC, right? So what I can do, I can bring C here, then I have B and C. So that gives me plus 1 over Z. And now notice that I have to contract C and B. So C and B gives me 1 over Z. And then I have a derivative acted both on C and derivative acted both on B. So what I can do, I can think that I have 2 derivatives acted on C, but there is an extra minus sign. So there is a minus sign, and then there is del Q. And so if you do the arithmetic here, what you'll find out is that this guy is 12 lambda over 2, that's the fourth. This guy is minus 2 over 2, that's the fourth. And so the same manner, you're going to do the last contraction. And for the third one, we're going to get minus 12 lambda squared over 2z. So now we are in a position to actually compute what the central charge of our BC system is. So the central charge is going to be equal to minus 2 coming from the first term, plus 12 lambda coming from the second term, and then minus 12 lambda squared coming from the last term. And so it's conventionally written as minus 3, 2 lambda minus 1 squared plus 1. Okay, so that's just an algebraic manipulation. So what we computed a holomorphic central charge. And then any CFT has both holomorphic and anti-holomorphic sector, even if the other one is trivial. So in order to compute a central charge in the anti-holomorphic, and I have to compute T tilde, T tilde. But remember that we define our CFT in such a way that those bars are zero. So we will conclude that the anti-holomorphic central charge equal to 0. So what we see an example of a CFT. So this BC system is a CFT where there is a difference between central charges in the holomorphic and anti-holomorphic sectors. So that's not the same. This is very different what happens in a theory of free scalar fields. So those CFTs are kind of very simple, so they have the same central charges, and this one is more interesting. So let me continue. Let me just continue talking a little bit more about the CFT, and then we go and discuss the physics. One thing that I want. So before I go any further, is that clear? Is the central charges and the stress energy tensor of the CFT clear? And I convinced you that that's the CFT with that funny weights lambda. Yeah. Yeah. How to construct the energy. Right. So we'll talk about that. We'll talk about this later today. So what I mean is, this is something which I know nothing about. I'm not a specialist on algebraic field theory, but I will explain you how to think about CFT in the algebraic context. So meaning that we will have a Hilbert space, and we will have a set of operators that will act on that Hilbert space. And so in some sense, what we will, at least my goal today, is to build up a structure that would be enough to talk about CFT in that context. So we might not reach that today, but that's where we are moving eventually. Because we don't want to deal with that Z variable. So we want to kind of remove the Z variable. See, in the Hilbert space, there is no coordinates. And that's where we are heading. Okay. So this CFT has a symmetry. So this is called Gauss number symmetry. So BC system has a Gauss number symmetry. And so this is a symmetry, so there is an action written somewhere, and you can check that if I transform del V by minus I epsilon V, right? So epsilon is a constant. Again, we're talking about global symmetries. And del C is plus I epsilon C, then the action stays invariant. This is pretty much an obvious statement. And so because that's a global symmetry, there will be a conserved current associated with that. And conserved current means that they decompose into holomorphic and anti-holomorphic piece. And so in this case, there will be only a holomorphic piece. And the current will be just minus normal order DC. I'm not going to derive that. That's something that we'll be able to do. Okay, so so in order to, so let's think about this operator. So this, strictly speaking, the way you can think of this is that your B field has a Gauss number -1, and the C field has a Gauss number +1, right? So that's the way to think about the symmetry. And so in order to get a better feeling of this conserved current, so in particular you might ask, not all operators are tensor fields, right? Not all have a nice OPs with stress energy. Stress energy tensor itself does not have a well-defined. It is not. It is not a primary field, right? So it has an anomaly in its OPs, and that's a central charge. So we're going to do the same exercise here, and so we're going to look at the OP of T and J. So again, I'm just going to extract the leading term and then write down the subleading term. So this guy is going to be equal. So I have del C minus lambda del C, and then I have -1 here, and then I have B and C. Okay? Good. So there will be tons of terms here in this OPE, right? And the largest singularity will come. So I have noticed that I have 2 B's and 2 C's, so I can make contractions. So the largest singularity will come when I do a pair of these contractions. So in the first case, I have del B and C, so I move this C over here, and I'm not paying a penalty of any signs, so that's going to be del 1 over Z. And then I left with the CB, and CB gives me 1 over Z. So now I'm left with the other term. The other term is minus lambda. So again, I move this C field over here, and then I have, actually, what's happening here is that this guy is del C, right? And so there will be 2 terms here. So if I have del BC, that's exactly the same as before. So it's going to be minus lambda del 1 over Z, 1 over Z, right? And then I have B del C. So the first one gives me minus. So remember that always C is next to B, but there is no derivative active of B. So I have minus lambda 1 over Z. And then I have del CB, so that gives me del 1 over Z. Okay, so that's a leading singularity. And notice that the leading singularity comes multiplied by an identity operator, right? So this is kind of similar to what was happening in the stress energy. Right? So what I have here, I have times the identity. Okay? And so now, if you do the algebra, you will find out that this guy is actually 1 minus 2 lambda over Z cubed. Okay. So you see immediately that it cannot be a tensor field, right? Because it has an anomalous term. And actually, there are if you go further, you will find out that there is a term 1 over Z squared J of 0 plus 1 over Z del J. Okay, so in order to get that, you have to work a little bit harder. Look at the subleading singularities, and so what we discussed today should be enough to do this analysis. And so you can see that so J is almost a field of scaling dimensions 1 and 0, right? Conformal weights 1 and 0, but not quite because of that anomalous term. And so now, once we know the OP, we can ask the transformation laws. How does our Bose current transforms under the classical transformations? So transformation law. So epsilon delta J. So it's to minus V del J minus J del V. So again, remember we had a discussion last time that once we know the singular transitor P, we can relate that to the conformal transformation property of the field. So there will be a minus V del J minus J del V, and then there will be additional P's, and this additional P's will come to lambda minus 1 divided by 2 del 2 E. Okay, so that last term will be the one that will produce anomalous 1 over z squared singularity, right? So this is exactly what's expected of a primary field. Conformal weights 1, 0, and the other piece is anomalous, and so as a result, if we have a finite conformal transformations, there will be additional piece, something like a Schwarzian derivative in the context of finite transformations of the stress energy tensor. And so let me just write it down. So finite form of conformal transformation. So there is a reason, you will see later today, there is a reason why we studied finite form of conformal transformation for the stress energy tensor. And believe me, there is a reason why we do that. And so the answer is that it tells that z prime, then I have j z prime, well, I write down j prime of z prime equals to jz. J of z, right? So if I have this, then this will be a primary tensor field of holomorphic weight 1. But actually, there is additional piece, and this is 2 lambda minus 1 to del 2 z prime over del z prime. Okay, so this is kind of analog of Schwarzian derivative in case we talk about finite transformation of the stress energy tensor. Okay, so these are kind of technicalities, and now let's discuss some physics. Okay, so what's that system is good for? So let's see. So we kind of, by doing this analysis, we kind of have in mind Polyakov action, right? The Polyakov action has the free fields on the world volume, and it has d fields, right? So there is a difference. Between Polyakov action and the CFTs that we are talking here. So in the Polyakov case, the Wolchit metric can be anything, right? So in the CFT case, we have a flat metric. So we can always locally make this change of variables, but we have to worry whether we can make a metric on a Wolchit of the string flat without any anomalies, okay? And the answer to that question is that, or in other words, whether our two-dimensional quantum gravity on the Wolchit consistent theory or not. And so the answer to that question is that it's consistent if total central charge, okay, so we don't want to have any anomalies in the stress energy tensor, because that would imply, what you will learn probably later, that there are problems of making a consistent gravity in this case. So what we want, the total central charge to be equal to 0. Okay. So the total central charge should be equal to 0. Then the theory can be consistently coupled to dynamical gravity. And so, so remember that what we already discovered. We discovered that for the Polyakov action, when we computed the quantization of that theory in the light bulb, we found the number d, right? So the number d was 26, so which corresponds that once we construct the corresponding CFT, so the central charge in a matter sector is going to be equal to 26, and that's problematic, so we have to make sense somehow. And in order to make sense somehow is to actually, and we will see exactly how it comes out naturally, to add something to the CFT, so we need to add another sector, right? So in other words, the covariant CFT of a string theory will contain 26 free scalar fields plus additional CFT, right? So it will be a direct product of two CFTs, something like, in this case, we actually have 26 free CFTs, direct product of them. So this other CFT will be a ghost CFT. And this ghost CFT is going to be our BC system with lambda equals to 2. Okay? So I will explain exactly how it will come up. We will actually derive this. But now, for now, all I want you to do is to do a tiny numerology. So we know what the central charge of a BC system is for any lambda. So when you compute the central charge of a BC system and you substitute lambda equals to 2, you will find out that that's equal to minus 26. Okay, so the total central charge, so this is an example of a CFT which has a negative central charge. And so the total central charge of a Walsh string theory in a covariant quantization will end up being 0. Okay. So that's one application of this BC system. So it will, and the way I keep telling that it will come naturally, the way how it will come naturally is that we again will look at the Polyakov action and we'll fix a conformal gauge. We'll fix a gauge so that the Polyakov action looks like this two-dimensional CFT with the fields. And in order to do that fixing that conformal gauge, there will be ghosts. There will be a ghost determinant. And that system, this determinant, we can rewrite as this additional CFT, which will end up being a BC system. Kind of similar to what is happening in gauge theories. When you do a gauge fixing, there is a Fourier-Popov determinant, and you rewrite that Fourier-Popov determinant as an additional piece to your action involving fermionic degrees of freedom, fermionic ghosts, which is exactly, as you can see, that's kind of parallel flows the discussion here. So that's one application of the BC system. There is another application of this BC system for which I'm just going to spend a couple minutes, and those of you who will continue studying the subject will have a lot of it. So what we're going to do, we're going to look at the case when lambda equals 1/2. Okay. So in this case, we have two anti-commuting fields, B and C, and notice that HB equals to HC equals to 1/2. And so what I can do, I can call B psi. Okay, so we'll be, this is kind of an implicit reference to fermions. Okay, Walsh fermion. I'm going to write it down 1 over square root of 2 psi 1 plus psi 2. And then I'm going to call C psi bar. Okay, I emphasize that those guys are still holomorphic, so I do not mean that psi bar is anti-holomorphic field. What I do mean is that there is simply a sign flip compared to the formula above. psi 1 and psi 2, psi 1 and psi 2 are holomorphic fields. So what will happen is that the action of the DC system will become in these new variables. I just did a change of variables. So it will decouple. So I will have now, instead of a single DC CFT, I have two CFTs, which is not a surprise because there is no difference between B and C fields anymore. So in fact, the way to see that it decouples, because when I compute the stress energy tensor, so if I compute the stress energy tensor after I make this change of variables, it takes the following form. So it's -1/2 psi 1 del psi 1 minus 1/2 psi 2 del psi 2. So in other words, the stress energy tensor is simply the sum of the stress energies of each piece separately. So the central charge, when lambda equals to 1/2, CBC, when lambda equals to 1/2, minus 3, 2 lambda minus 1 squared plus 1. So that was the general formula. So if you substitute lambda equals 1/2, you will get 1. Okay? And so what you see that actually, for this particular value of lambda, we have two CFTs, and the central charge of this psi 1 is equal to 1/2. So what we just discovered with you is that free world-shaped fermion, a single free holomorphic world-shaped fermion, is a conformal theory, and it has a central charge 1/2. So this, I'm not going to discuss any further, but that you can imagine that the whole subject of superstrings involve a CFT, where for each bosonic degree of freedom, we actually add a fermionic degree of freedom. So the only thing I'm going to say is that so a single, if you wish, a single world-shaped supermultiplet C matter superstring. So again, I need to have one bosonic degree of freedom, and I need to have fermionic degree of freedom, because supersymmetry is a symmetry which relates bosonic and fermionic degree of freedom. So a single supermultiple will have a central charge 3/2. Right? So one will come from bosonic fields, and 1/2 will come from a fermionic field. And actually, the whole discussion of CFT will extend in the context of conformal CFT as well. So one last, so before I go any further, any questions about DC system? No? Good. So something that I'm not going to discuss, I'm just going to mention because at least you can appreciate, well, kind of going into physics immediately, discussing what will happen, is that, so you know that the way to think about DC system is that when we fix conformal gauge in a bosonic string, my claim is that we will see that DC system will show up as a determinant, a Popov determinant in fixing the conformal gauge. Now, in the case of a superstring, and remember, we need to do the superstring, otherwise we will have tachyons in our spectrum. We need also fermionic degrees of freedom, and so there will be additional gauge fixing, if you wish, associated with that. And so once I do the gauge fixing in the superstring, there will be a gauge fixing in the bosonic sector. That will be a BC system here. And then there will be a gauge fixing in the fermionic system. And the gauge fixing in the fermionic sector is what's known as beta gamma CFT. Okay? So it will come up as beta gamma. So I'm going to write down the general beta gamma system, kind of similar to in Fourier-Popov determinants. There the ghost system that shows up is with lambda equals to 2. So here there will be a specific number as well, but I'm going to write it down for arbitrary lambda. But you can sort of guess the parallel, right? So in fixing the gauge symmetry for the bosonic fields, we have to introduce a fermionic CFT, right? So now I'm telling you that this guy will come after fixing gauge symmetry in a fermionic sector. So B gamma system is a bosonic ghost CFT, right? It's kind of it works opposite, which is something you expect, and the action is actually very similar. So again, it's a holomorphic CFT. It takes this form beta del gamma, and because it's a bosonic CFT, the field beta and gamma actually commute. Okay, so you can go ahead and develop the whole machinery again as we did for the VC system. Well, so it's holomorphic. And then the only contractions are again between beta and gamma. So it's -1 over z. So it's exactly the same as with VC system apart from some signs. And then gamma and beta is going to be equal to 1 over z. Notice that beta gamma, there is now a sign flip. And the sign flip because there is a coordinate dependence order changes and the fields are commuting. So it is not compensating by anti-commuting fields. So the stress energy tensor takes exactly the same form as in the VC system. So it's del beta gamma minus lambda del beta gamma, and anti-holomorphic part is 0. And again, you can go ahead and compute their central charge. You will find out C equals 2 lambda minus 1 squared minus 1 equals to 0. And so in a superstring theory, what will happen in superstrings? What you will encounter, a beta gamma system with lambda equals to 3 half. All right. All right, guys, so we are done with a dirty worldsheet analysis, and so now we move to better places. We now move to a Hilbert space, and what we want to do, we want to think about the CFT as, having a set in Hilbert space and having a set of conserved charges, a set of some operators that acts on the Hilbert space. Okay, so the next topic is going to be Virasoro algebra, and so what we will see, so what we saw before is that there are lots of conserved currents in the CFT. Right? So we all get lost at some stage in algebra, but let's keep the general picture clear. So remember that in the CFT we had an infinite set of currents, right? So so the stress energy tensor is holomorphic, and once we know the holomorphic stress energy tensor, we can construct a conserved current which is minus V of z T of z, and so there is an infinite set of conserved currents. So the point is that for each, you know that if somebody tells you that there is a conserved current, there must be a conserved charge. So there will be an infinite set of conserved charges. Corresponding to currents. And so what we want to do, we want to think about the CFT as a Hilbert space and construct this infinite set of conserved charges. And those charges will be an operators that act on the Hilbert space. All right, so that brings us to the discussion. So those charges will be interesting objects, right? So much like I call charges, but you can think of them as being operators, right? Because you know in quantum mechanics, operators are not commuting in general, and this acts by interesting algebras. And so in this case, we will discover also interesting algebras, and so what we are after are various Virasoro algebras. Good. So, go ahead. So remember that we had open string, and we had closed string. So I'm actually going back to sigma 1 and sigma 2 variables. Closed string. So we have sigma 1, which was space, right? So we have sigma 1 and sigma 2. Well, actually, I'm sorry to write it. Usually we write down time first and then space. But here, this guy is space. Spatial coordinate, this guy is time. Okay? Which is Euclidean time. So in the case of open strings, remember that our sigma 1 was going from 0 to 5. And in the case of the closed strings, sigma 1 goes from 0 to 5. And sigma 2 is Euclidean time. So sigma 2 is from minus infinity to plus infinity in both cases. Okay? So everything that I'm going to talk about and we're constructing the algebra will be for the closed strings, and I will talk only about the holomorphic sector. The extension to anti-holomorphic sector is trivial. The extension to open strings require a little bit thinking, and that thinking is after you read Joe's section, and the little thinking involves all these doubling tricks that you have to do a little bit. But in principle, there is a straightforward extension of everything that we will talk to open strings. But I'm not gonna talk you to time. Okay, so let me go ahead and introduce two different types of conformal complex coordinates that I used in CFTs, and I will well, actually later maybe will be clear why there are two are, because some of the questions are easier to ask in one framework, and the other ones have a simple answer in the other one. But the important thing is that the two complex variables, so the first one, omega is sigma 1 plus I sigma 2. So the second one is that variable, which is e to the minus I omega, right, which is e to the minus I sigma 1 plus sigma 2. So first of all, notice that they are related by a conformal transformation, right? So introduced by a holomorphic transformation. So these are conformal transformations. And so what is conformal transformation are doing for you, right? So in this picture, so our worldsheet, so there is a sigma 2 coordinate, right? For imaginary part of omega, right? And so this is our worldsheet time, right? So this is a time, and this guy is space, so 0 to pi. So in this way, when we talk about omega coordinate, we talk about the cylinder, right? So those two ends must be identified. So in this complex coordinate, our worldsheet and the CFTs that we talk about is just, you can think of this as a loop. This is a very intuitive picture, a loop propagating propagating in time, especially if you identify the world-sheet time with the space-time time. And so in particular, in this picture is useful when we talk about the Hamiltonian. So Hamiltonian is time translation, is in omega translation. Right? So in this picture, there, what do we call the Hamiltonian of the system is a translation of the Euclidean time. So, so now I told you that in order to go from this framework to this, what you do conformal transformations. And so, so you can easily convince yourself that what will happen is that in doing this conformal transformation, you kind of squeeze this n at minus infinity, and you expand this n to the plus infinity. Because now in this case, so this is that plane. So those circles are going to be or angular coordinates are our spatial coordinates, right? So angular, you have to think symmetrical coordinate system is a polar coordinate system, and so our time. So this is time. So time runs radially, right? And so an angular angular coordinate is space, right? And it has a natural periodicity of 2 pi, much like we did for the periodicity of our closed strings. So the origin is time minus infinity, and actually you can see this also explicitly by looking at the change of variables. Okay, so this z coordinate, this framework, right, is the one that we've been developing all our CFT, right? So we were talking about the CFT and Z bar on a complex plane. So up to now we were leaving here. But eventually our idea is to think about the Hilbert space, understand the dimensional operators, understand masses in the spectrum. And so what it means that we would have to, at some stage, to at least ask some questions in this picture, because here we have a notion of the Hamiltonian that will determine for us energy. Okay, good. So, but as I said, notice that everything we ever did with the CFT was in this Z system. So this Z coordinate system is more suitable for specific computations. And you can get answers by just making conformal transformations. All right, so let's go ahead, and I'm going to introduce a notion of Virasoro generators. So by definition, so this is going to be fine. So T of Z, remember the stress energy tensor for CFT is a holomorphic function, right? Which means that I can write down a Laurent expansion for it. I'm just going to write down a Laurent expansion in this way, sum from minus infinity to plus infinity. Then I have Lm divided Z m plus 2. So in this case, notice that those Lm, they are coefficients of the Laurent expansion, and they do not depend on Z by definition. Okay, so Lm are coefficients of Laurent expansion, and they are actually called Virasoro generators. Okay, so now you know what a Virasoro generator is. And you will see in a second why those Virasoro generators are so important. By definition, okay, so this was the definition, right? So how do I compute the Virasoro generator? Well, easy, right? All you have to do is to compute an integral around the origin, right? So if I have a closed contour around the origin, then this will sort of generate that is equal to 2 of z, right? So you can explicitly count that if you have that Laurent expansion, the coefficients of the Laurent expansion are given by the contour integrals, as I explained. So I'm not going to talk about this, just don't even try, but of course there is an extension to an anti-holomorphic sector in the natural manner. Okay, so there is T tilde and L tilde. Okay, so so eventually, the stress energy tensor is related to a Hamiltonian, but notice that this stress energy tensor was written in this z coordinate system. So we have to go back. We have to go back to the omega coordinate system, and so we have to know how the stress energy tensor transforms. Well, that's a holomorphic change of variables. So what will happen is I have the stress energy tensor T, which is actually TZZ component. And so once we do this change of variables to the omega frame, we get the stress energy tensor with the indices omega and omega. And we know exactly how it will transform, because we know exactly how the stress energy tensor transform on their arbitrary conformal transformations. Well, so there is a familiar piece, a simple one. So it will transform as del omega z squared TZZ. Okay, so that's a tensor transformation property on the conformal transformation, and that would be it. If our stress energy tensor would be a primary field, but it's not the case. Remember, there was plus Schwarzschild derivative. Right, and you can easily compute what the Schwarzschild derivative is once you know what the change of variables is, and there is a change of variables given by explicit function. So if you do that computation, you will find out that that there is an additional term in going from the plane to the cylinder, and that additional term is central charge divided by 24. So what is happening is that we might ask the question, so we have a Laurent expansion there. What the Laurent expansion corresponds to the expansion on a cylinder? And the answer, Laurent expansion is that. So it will correspond to a Fourier expansion on a cylinder. So you can easily follow and follow the analysis, and you will find out that you can pretty much see what will happen with terms of the Laurent expansion of the stress energy tensor. So the stress energy tensor in omega frame will depend on omega variable, and it will be given by the Fourier expansion. So I have e to the I m sigma 1 minus m sigma 2, and then here I have coefficients t sub m. Those are coefficients of the Fourier expansion, and those coefficients are the ones that will be related to Laurent expansions. So this Tm you will discover equal to Lm. Those are exactly the Laurent coefficients. And there is an additional correction, though, minus m comma 0, 0, 24. And let me write down the anti-holomorphic sector here as well. So it's Lm So there is a shift. There is a shift for the zero components, and you can see why that is the case, because there is an anomalous omega independent from here, and so there is this shift associated with the central charge. Okay. Another thing I want to bring to your attention is that, of course, this is something that you will discover if you do this transformation on your own. Notice that there is m plus 2 here, right? So the Virasoro generator Lm is a coefficient of m plus 2 term. And here, you know, in general, it's related to a Fourier coefficient Tm, but this Tm is not m plus 2, right? It's actually m, the m's coefficient of the Fourier mode. And the reason for that is that this factor of 2 here. Okay? So this is del z over omega, del omega over z is equal to minus iz, right? So if you square it, you will get minus z squared. So that z squared will cancel precisely the square, here. And so once you go to this omega coordinate, there is no m over 2 here. Okay? Right, and actually you can also see where this minus sign comes from. So this minus sign comes because of I. So once I square, I will have I squared. So I pretty much told you already how to derive that. All right, so any questions so far? No? Okay, so very good. So now let's ask the question, so what are those Virasoro generators good for? And why should we care about them? So that brings us to the discussion of conserved charges. What we will end up showing is that Virasoro generators are actually conserved charges, and there is an infinite set of them. So this is an infinite set of conserved charges associated with conformal symmetry transformation. Okay, so we will now go ahead and compute commutation relations once I introduce the notion of charge. So commutation of conserved charge. Okay, so first of all, suppose I have a current, J of Z, so it's a holomorphic current, so it's conserved. So J of Z is conserved current. So in the Z coordinate, it simply means that it's holomorphic. So what I can do, I can construct a charge, and so I will construct a charge, and this charge will depend on a contour C, and I'm going to define the charge by taking a current and integrating it around the contour dz over 2 pi r J of Z. So why do we call so I claim that this is a charge. This is a conserved charge. And so I want to explain why do I call it a conserved charge. And the picture is very simple. So what I have some contour C, right? And I'm computing some contour integral. But my integrand is holomorphic. So whether I take this contour or I take a deformed contour, I will get the same answer. Or if I take contour C1 and then contour C2 and then contour C3, right? So as long as this guy as this guy doesn't have any singularities, what will happen is that it's going to be independent. The charge Q will be independent whether I compute it on contour C1, C2, or C3. And the reason for that is that that's a holomorphic integral. It doesn't depend on the way the contour is drawn. So in other words, provided there is no singularities coming from operator insertions, and we will see in a second what we mean by that, then Q at the contour C1 equals Q at the contour C2 equals Q at the contour of C3, right? So they are all the same, so in this sense it's conserved, but normally we say conserved with respect to time. Now, what is the difference between the contour of C2 here, C1, C2, and C3? Those are contour at certain fixed radial distance, right? So, and what I'm doing to go from C1 to C3, I'm increasing the radius of the contour. So the Euclidean time T1, T2, and T3. So the fact that it doesn't depend on the contour means that it doesn't depend on the time, on the Euclidean time at which I evaluate. So that's why it's very natural to think of this as really a conserved charge. It's something that doesn't depend on time. Normally what we do.
So
yep.
C's, they're all going to be circles, or can they be arbitrary contours?
It doesn't matter, right? Because as long as there are no singularities, I can choose it wherever I want. And moreover, computing contour integrals of holomorphic function boils down to computing the residues, right?
Right.
So that doesn't really matter whether it's circles or not.
Right, but if you want to evaluate it at one specific time, then it has to be circular.
Yes. But again, you have to think that our series. So when I do that kind of cylinder, what I'm doing, I'm telling you a preferred time direction, right? And remember that we're talking about relativistic theory with well, it's no longer Euclidean Lorentz invariance, right? So what I'm trying to say is that I can do various boosts or choose a different time slice. And so by drawing contour in a different way, I would say that it's still conserved with respect to time, except that the time will be different, right?
Okay. So there'd be a certain observer that would see this.
Right. Yes, exactly. So this is, if you wish, an observer for which the time is very simple. It's just the side of the cylinder, right? The height of the cylinder, running along the height of the cylinder. But any deformed circle on the Z frame will correspond to a different way of introducing time in the picture. Okay, very good. So what I want to do now, I want to compute the following thing. So up to now, there was only single current, and there was single conserved current, and there was a single conserved charge. So now I'm going to introduce two conserved currents, JI, right? So I equals 1 and 2, and correspondingly, there will be Q1 and Q2. And so what we are after, I want now to compute a commutator of conserved charges, right? So I want to know. So the question we are ultimately. So if I think about these charges as operators acting on the Hilbert space, so our question is, what is the commutator? How do I compute the commutator between two conserved charges? Okay. And I will put a hat to denote that that's an operator rather than a contour integral. So everything we did before that was just a contour integral. All right, guys. So before I do that, I have to go back. To something that you all must know, which is quantum mechanics and the path integral of representation of quantum mechanics, and going from path integral to a Hilbert space. So I'm just going to give you a 5 to 10 minute stops that we need, and because otherwise it might be Yeah, it will be easier to fall in track. So relation between path integral and Hilbert space. Okay, and so I'm sure that many of the words I'm going to say you know, but I just want us all to be on the same wavelength. Well, so a path integral. So let's look at quantum mechanics of a single degree of freedom. So I have Q of t. So I can look at the path integral, right? So I'm going to study so I'm just going to study the following process. So I start at time t equals 0 and t equals capital T. So there is Q of 0 here, and there is another one. So I'm just going to write down this Q0. I'm just going to write down this guy Q capital T. And so the whole idea behind the Feynman path integral is that we want to compute an amplitude, a transition amplitude, given the prescribed boundary condition, right? So we must start at time t equals 0 at Q naught, and we have to end at capital T at Q of t. And so in the operator language, what do we have? We have a transition amplitude. So on one hand, we have at time t equals 0 and Q0. So here we have time t, and we have ordinate Q sub t. And so this transition amplitude is given by a path integral. So a path integral, I have to integrate over all smooth these. Well, I mean, there are various mathematical ways to make it rigorous. So typically we require some continuous passes. That's usually enough. So continuous passes, and then what I have to do, I have. Let me see. Well, let's talk about Euclidean time evolution. And so then I have an action, right? And so the path integral. So here I have S of Q. So the path integral with the prescribed boundary conditions, that I look at all passes such that at t equals 0, it's Q naught, and Q of t is equal to Q sub t. And so this path integral gives me an amplitude of the transition between 0 to naught and t, Q sub t, right? So is that correct? Right? So the starting point is the same for all of us. Good. So what I'm going to do now, I'm going to do the following thing. I'm just going to cut this integral. And when you read Polchinski, he talks about cutting the path integral. Okay, so that's what we're going to do. So we're going to cut the path integral at t equals to tau. Right? So all our passes are continuous. So in particular, so if it reaches here, it must start from here to go to there, right? So, so what I want to do, I want to write down this path integral, or this amplitude. I'm going to call this final state. This is initial state, right? Final initial. So I can write it down as a path integral. So first of all, there will be two path integrals. But there will be three integrals altogether. So I'm just going to write down dq of t, dq prime of t, right? Not a good way. So what we're going to do first, we're going to first compute an integral e to the minus s, e to the minus s, and so in computing this integral, so this is a path integral, this is an integral over all functions, and I'm going to make the following boundary conditions: q at 0 equals to q naught, and then q of tau, right? So in this, so in the action, I forgot which it was written. So this is the action from 0 to t dt of the Lagrangian, right? So here I will have minus an integral from 0 to tau, right, dt of the Lagrangian. So I'm going to look at the passes that start at 0 and end at this intermediate point. It goes to tau, so q of tau equals to q tau, right? And then I have to propagate it further. So I have to consider an integral e to the minus. So here I have an integral from tau to capital T dt of lambda. So again, this is a path integral with the boundary conditions at tau equals q tau, and then q of t equals to qt, right? So there is additional integral. So remember, those two are kind of obvious, right? So I propagate to this point, and then I go to the end point. However, there is an additional integral, because if I leave it like this, then I'm just going to consider the path integral where time t equal tau all passes pass through this point. Now, in order for me to look at the full path integral, what I have to do, I have to integrate over these spatial points. So this last integral is actually ordinary integral with respect to this dq tau, right? So it goes from minus infinity to plus infinity, right? So that's this intermediate ordinary. So what's the meaning? What is the meaning that we did here? So in the Hilbert space language, what we did, we started with the initial state, right? And then we propagated that initial state up to a final state. And the final state is now our q tau state. Q tau state. So that's what this first pass integral is doing for us. It propagates the initial state up to q sub tau. And then the second one starts with a state q sub tau, the same state as being prepared here, and it propagates us to the final state. Okay, so that's the two pass integrals here, and then we are left with an ordinary integral here, dq tau, and actually you can see now. So here I give you an argument using a pass integral language, but here is actually an argument using a Hilbert space language, because what I have here is a final state, and then here I have an integral of dq of q state, and then an initial state. Right, so what I did between initial and final state, I inserted the complete set of states. Right, so this integral is complete set of states. Okay, and complete set of states is actually an identity. Right. So what we derive this simple notion in the language of the path integral. Okay, so any question so far? So, okay, so now something that we used before, and I assume that you know that, but now we can actually make sense of it in this picture. So what I can do, I can now look at the following path integral. I'm just going to look at the path integral dq e to the minus integral from 0 to capital T, right? dt times L. And so now what I'm going to do, I'm just going to introduce q of tau. So there is no integral, so I inserted a function there that depends on my coordinate in the path integral q. And so what is the meaning of this path integral? So I can do the same manipulations as I did there. So I can break it as, I can write it down in the following way. So I can break it up to this time tau, and then from this time tau up to the capital time t. So I will have an integral over dq, right? And then what do I have here? I have here final state, right? So here I have my q state, and then there is a q, and then there is a q state here and the initial state. Okay. So this is a path integral, where in the path integral I integrate up to tau. In this one I integrate from tau. Okay. And so this guy depends on tau, right? However, when I write down this way, what I mean, I can think of this as this is a state in a Hilbert space. So this is a state in a Hilbert space, which is an eigenstate of an operator Q. Okay, so now I introduce an operator Q. It doesn't carry any time, and the point is that when I add with Q on the state Q, then I'll just get Q. Q is a state Q back. So in other words, as I said, this Q is an eigenstate of the operator Q. So once I do that, then what I can do, I can actually rewrite this integral in the following manner. So I still have to integrate over all the Q. So here I have F, and then I have my operator Q hat acts on Q, and then I have Q and initial state. Okay? So you can see now that I have a complete set of states here, right? And so I can integrate, well, actually, to be more precise, this is actually an operator that would depend on this time tau. Right? But I can integrate over, I can perform this integral, and this integral gives me 1, much like in the case there. So what we end up finding, something that we used many times before, if there is an insertion inside the path integral, then that's the same as a corresponding operator acted on the initial and final states, which are prescribed by the boundary conditions when we talk about the path integral. So in other words, so that path integral corresponds to this matrix element. Okay, so the next step, and that's what actually will be crucial for us, is okay. So is it clear what I said? Was it boring? Did you use that already? Okay. You want me? So there are two things now. So I can go ahead and tell you that, but I have to say that everything that I said is enough to just repeat the same arguments in the case when you have this path integral. So now I have this path integral to the 0 to t dt, and then I have q of t1, q of t2. So at the end of the day, if you ask if I have two functions, q of t1 and q of t2, what does that correspond to in the Hilbert space language, and which you will find out that it's this. Where t is a time ordering. Okay. So do you want me to show this, or it's more or less? Okay, good. So, but I did the first steps. What you have to do, you have to cut the integral not once, you have to cut it twice, and you will have, instead of introducing a single set, full set, set of states, you would have to do it twice. Okay, and then you will end up finding that whenever you insert functions inside the path integral, they come up naturally as being time ordered. Okay, so let me derive something. So now we go back to our conformal field theory, so now I'm going to talk about a preferred time direction, and I'm going to talk about correspondingly preferred time ordering when my times are circles, corresponding to nice circles, which is corresponding to that beautiful line. So, let's let me explain exactly what kind of what I want to compute, and you will see why that will end up as being a commutator. Okay, so I'm going to have three contours. Okay, so now I have two conserved charges, right? And I have three contours. So on the Z plane, so this is 0. There is C3, right? And then there is C2. And then there is C1. Okay? So what I'm going to insert is a path integral. I'm going to insert Q1, right? So Q1, remember that, so we now have two conserved charges, right? So corresponding to two currents. So I'm going to look at Q1, which is an integral over contour C1. And then there is a Q2, which is evaluated as a contour C2, right? So this guy goes first, this guy goes second, right? So this one is earlier in time. This guy is later. Okay? And then I'm just going to subtract. So then I have minus Q1 of Q2 of C2, right? And Q1 of C3. Right? So again, the first one is the one that goes earlier. And this one goes later. So what I'm doing, I'm just going to, and each of these symbols is, it's erased, right? Well, I have another. So each of these symbols just an ordinary integral over some current, and we insert it in the path integral. So once we inserted this in the path integral, those guys become operators, much like we discussed here, and they become a time-ordered operators. And I already time-ordered them for you. So moreover, those operators do not depend on time, so those are conserved charges. So I'm going to drop any time dependence. And so what do I have? I have Q1, Q2 minus Q2, Q1. So in other words, when I evaluate this in the path integral, then what I'm evaluating Q1 times Q2 minus Q2 times Q1. So in other words, I'm evaluating a commutator between two conserved charges. So is that clear? Yes.
You have C3?
Yes, I have C3, which is here. So C3 is earlier. That's why it comes first. And so it's a Q1 charge evaluated over contour C3. and then Q2. See, this 1 and 2 has nothing to do with the contour. So this one simply corresponds that I take the conserved current J1 and integrate Ez over 2 pi I over the contour. Sorry. So I do have 2 charges, Q1 and Q2, but I have 3 contours. Okay, and so so what is happening is that I play with contours in such a way that the corresponding operators will, this combination will now end up producing the commutative charges. Right? So I did a time ordering there, and so in a Hilbert space language, that would correspond to the same ordering of operators. See, the thing is that up here, the order is not important. Right? Those were just, those were not the operators. Right? So those were our fields. But on a Hilbert space, ordering becomes important. Because that, in order to go from this line to here, I have to go through the machinery of the path integral. Okay, very good. Very good, guys. So that's a good place to stop. So we'll stop here and take 10 minutes. We'll continue.